Okay, guys, let's go ahead and get started. Just a heads up, this class, so my Monday, Wednesday discrete class, your exam one grade should be posted on Blackboard this evening. So don't worry about them not being there right now. They'll be there soon. I apologize. Between my roommates getting COVID and having to quarantine and going to the doctor, it's been a pretty hectic week for me. So I apologize for not getting your grades back yet, but those should be up later today. Okay, so today we're going to start the chapter on algorithms. So in your Xi books, this is chapter 7.1, and then if you're following along with Rosen, discrete math and its applications, that's chapter 3.1. Okay, so many problems in mathematics and computer science boil down to describing procedures to solve the given problem, right? And this roughly translates to what's called an algorithm. So let's look at the formal definition of an algorithm. So an algorithm is a finite sequence of precise instructions and for performing a computation or for solving a problem. Okay, so definition of an algorithm, and have to emphasize that this is a finite sequence of precise instructions. Okay, so the properties of an algorithm, so algorithm properties. Okay, so every algorithm is going to have an input, output, it should be have a property of definite. So this means that each procedure is well defined. Okay. Correctness meaning that it returns the correct solution. To the problem or the computation. Finiteness so the algorithm terminates in a finite number of steps. So the algorithm uses a finite number of steps. and generality. And by generality, I mean that the algorithm doesn't just apply to a given instance of input, but to a broad range of input that all match the same criteria. Okay? So let's look at an example. I think that's the best way to get our heads around what an algorithm is. Okay? So describe an algorithm that finds the maximum element in a finite list of integers. Okay? So you're given a finite sequence or a finite list of integers. We want to find the maximum element in that sequence. Okay, so the way that we're going to describe this is what's called pseudocode. So solution with pseudocode. Okay. I always do that. Pseudocode. Okay, so pseudocode is just a general description of an algorithm in terms of steps, and it's going to vary based off of the textbook or the paper that you're looking at. There is no universal way of writing pseudocode, so you're just going to have to adapt to the pseudocode that you see. As far as my lectures go, I'm going to follow the same format throughout. And the way that this is going to work, I'll demonstrate with this example. So I'm going to start with the name. I'll call it find max element. Okay, so I'm always going to start with some type of name. And then the next part of the input is going to be my input. Okay. Now, here we're going to say maybe A1, A2, dot, 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 AN, a finite list, or I'll say finite sequence of integers. Okay. And then next, I'm going to say output. I'll say max. The maximum integer in the sequence of A1, A2, okay. And the next step will be to write the actual algorithm. Okay, so let's go ahead and write this out now. So we're going to let's start by defining max to be equal to the first element in the list. That says A1 right there. Okay? And then we're going to use what's called a for loop. So for I equals 2 to n. So maybe I should replace this by saying a finite sequence of n integers. Okay. Where maybe n is greater than or equal to 1 or 2. Okay, so this for loop is going to check each I from 2 to n. Okay? Maybe if I'm going to change the glare a little bit. Okay? All right, so for each of these I, we're going to check. So we're going to do if AI greater than max, then we can say max equals to AI. And then at the very bottom, we're going to say turn max. Okay, so let's see how this. So notice that this code here is not language specific, right? It's not Python code, it's not C code, it's not C++ code. It's just a set of instructions to solve the problem. It's pseudocode. And it's up to you to take something like this and to translate that into whatever language that you're programming. Write this down, make sure you have that like next to you, and then I'm going to pull up Python on my screen, and we're going to write this program, or write this algorithm. And if you didn't get it down, I'm going to write it again here in a second. Okay, so anaconda, spider. It'll take a second to open. It might be especially slow right now because I have a deep learning program running in the background right now for my machine learning course. And actually, I'm going to show you what that looks like just so you can see it at the end of today's lecture. Okay, so I'm in my my directory, my project Math 2305 practice. So I'm going to go ahead and I'm going to make a new script here. So I'm going to go over here, right-click, new file, and I'm going to call this find max in list.py. All right, so we see if that appears over here. Okay, so let's go ahead and recall the algorithm that I wrote down. So I'm going to do this by first, just like stating again, So main find maximum in a sequence of integers of integers n greater than or equal to 2. Input I'll give this a name like L is equal to A1, A2. So remember that Python, the indices of lists start with 0. So I'm going to change this 1 to a 0, change this to 1, dot, 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 up to A of n minus 1. Just so it matches up with Python. So max is a keyword in Python. Like if I come over here and I type max, you see that it highlights. It's a keyword, so we can't use max in Python, but I can say maybe maximum. I forgot to say, let me just change this around. That was the name that I wrote down. So just making this look nice. The maximum integer in the list L. Okay, and then we can do our algorithm now. Now this is not code, this is just comments for me to come back to. Maybe I'll space it out. Okay. So inside of here, I'm going to say maximum. I'm going to assume that's equal to the first one, 0. And then for I equals 1, so we've already looked at this one. Now we're going to look at this one and then go all the way down. So for I equals 1 to A of n minus 1. So this is again the pseudocode. This is not in Python code. So if a 0, or no, so a I greater than maximum, maximum equals a I. And then return maximum. This is the pseudocode. So in this script, we write an algorithm for finding the maximum in a finite sequence of elements. Okay, so that's what we're doing in here. All right, so we're going to write this as a function, as you will do often with algorithms. So the way that you do that is by saying def, and then we'll call this find maximum. L. Okay. Put a colon there, and now we're inside of the algorithm. So we're going to assume that, so we're going to say maximum is equal to L0. Okay? So that's like this part of the pseudocode right there. So then we need a for loop So for example, if L is equal to 2, 1, 10, 4, length of L is like, so this is, there's 4 things in here, right? So we can say something like n is equal to the length of L, okay? And then say for I in range, start at 1 and go to n, but this really goes to n minus 1 if you recall the range function. So if I just come over here and say n is equal to length of L, I'm going to do I in range 1 to n, range I, let's just make sure this does. So 1, 2, 3. So the range function, the second argument here, you're going to go from 1, 2, 3, all the way up to this number minus 1, which is exactly what we wanted to do with our for loop. Okay, so let's tab in here, or 4 spaces. And then we're going to say if Li is greater than maximum, maximum is equal to Li. Right, get it there, and then return maximum. Right. So hopefully everyone sees how this is working. So we're just scrolling through all these integers I from 1 to n minus 1. And then if the ith element in the list is greater than maximum, then we reassign maximum to be this element. So this is going to check each element in the list, and if we ever encounter one bigger than this one, we update it, and then if we encounter that again, we update it again. So let's look at an example. Say L is equal to like 10, 3, 12, 6, 7, 2, 21, 19, or something like this, right? The maximum we can see is 21, and we can say print find maximum of L. And this L didn't have to match up with here. I could just usually just call that capital L list. And it won't matter, right? Whatever goes in here is going to be evaluated in here. If we just pass this list, which is just some random list in there, let's see what it does. 21. So we see that we found the 21 in there. Okay. So what's nice about writing scripts that do this is that once you save that, so I just saved it, notice the star goes away. In here, I can say from find max in list, import find maximum. So what this does is this imports the function find maximum into our console, and we can also do this with scripts as well. So for example, we just take some whatever list, Q, and then we can just call our function find maximum of Q. Okay. Okay, so this is implementing is about as close as we can get to the actual pseudocode. However, in Python, we can do this a little bit differently. So we can say, like max is already built in to Python, right? And you should use this over your own code whenever possible. But let's just look at another way to do this. Find maximum 2 or something. So it's going to take in a list, capital L list, lowercase list is a built-in object in Python, so we can't use that. So, okay, so I just want to illustrate that whatever you put in, whatever you pass into the function, it doesn't matter if it matches what's outside of it. So because list is a little bit close to this, I'm going to go ahead and change this back to just L. Okay. Okay, and then make sure. All right. All right, so let's look at another way of doing this. So we could say maximum equals L of 0. And then we could say something like for A and L, if A is greater than maximum, maximum equals A. And this because L is an iterable object, and we can just scroll through all the things in L and check to see if they're ever bigger than maximum. If we ever encounter one bigger than maximum, we update, and then it checks the next one. If it's bigger than maximum, then we update. So this would be another way of doing it here. So we run that. So this here, whenever you run, when you press play on these scripts, these functions are automatically imported into your console, and this just imported it again. That's all it's saying there. So let's try the new one we just wrote. Find maximum 2 of Q. And you see that it's singles. Okay. So I think those are the only two ways that you could change it up a little bit, other than just using the built-in max function. Yeah, I'm trying to think if there's another way of doing it. No, those are the only two ways I can think of. Okay. So next, we're going to consider searching algorithms. So given a list of items, it's often the case that you want to search for a given element. Okay. So okay, so let's see. Problem. So locate x in a finite sequence of integers a1, a2, to negative. Okay. So we can write pseudocode that should solve this problem. Okay. And this is called linear search. So as an input, we have x, which is an integer. And then we have a1 dot 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 to an, a finite sequence of integers. Okay, with n greater than or equal to 2. I should probably modify this problem a little bit to say distinct integers. So there's no repetition. Okay. And then our output is going to be, let's say, call it location. And this will be an integer. So an integer index say an integer index I, where x equals a sub I if I greater than or equal to 0, and I equals -1 means x is not in the list. They're not in the sequence. Okay. So then the algorithm okay. So what we're going to do is we're going to say location equals to 1. Okay. And now we're going to use what's called a while loop. So while say location this is too big of a name for an index. I'm just going to call this index I. It's an integer index I. Okay, it still works. So we'll start with I equals to 1 and then say while I is less than or equal to n, and a sub I is not equal to x, I equals I plus 1. Okay. Oh, this says and right here. You can't see it. It says and. So while I less than or equal to n and a sub I not equal to x, I is equal to I plus 1. Okay? So then after this while loop breaks, because eventually we're going to get to either n or we're going to have a sub I equal to x. So if I less than or equal to n, so that means that we broke out of this while loop before n or at n, or this might need to be, right, so if I is equal to n and then we go to I plus 1, then that would be bigger than n, it's fine. So the only way that we're going to break out of this and have I less than or equal to n is if we found x inside of this, the sequence. So if I is less than or equal to n, return I, else, as an if else statement, return -1. Which means that we didn't find the, so if I was equal to n plus 1, we never found it in our list. So if I is greater than n plus 1, or greater than n, so that's the else part of this if statement, then we return -1 to mean that it's not in the sequence. Okay, so this is called linear search. So let's go ahead and program this. Okay, so let's make a new script here. Call this linear search.py. All right, so we're going to do just as we did before. We're going to have a description that looks kind of like this. I'm just going to copy that, paste it. So in this script, we implement linear search. So here we have x, which is an integer. And then have a list L, finite sequence of n distinct integers. In our output, we'll call it I. So this is an integer where I greater than or equal to 0. Again, translating back to Python, since indices start at 0 for this in Python. So where I is at is the index location of x and L. And I equals to -1 means x was not found in L. Okay, so let's go ahead and write our pseudocode here. I is equal to 0, so that's the starting index in L. And then we're going to say while I less than or equal to n minus 1, and a sub I not equal to x, I equals I plus 1. We just increment I. So then here, if I is less than or equal to n, or n minus 1 in this case, return I. Else, return -1. Okay. Okay, so let's go ahead and do this. So write this as a function again. So def, call it linear search. We'll say x, and then list L. We'll say I is equal to 0. And then while I less than or equal to, so I'm going to go ahead and get n in here. This is the length. So n is equal to the length of L. So we're n minus 1. And then end L at I not equals to x, I plus equals 1. So this is how you increment I. And here, if I less than or equal to n minus 1, return I, else return -1. All right, so this looks like it'll do it. I'll save that, run it. So I have several lists here, and I have my linear search. So I can say linear search. Let's find the location of 6 in L. So 6 in that list L, this list right here. 3, and let's check it. And that is the location. Let's see. So let's see if 20 is in L. So linear search. -1 because 20 is not in that list. Okay. So this is a nice function that implements linear search. Very simple. It just checks all the indices in L, and if we ever come across an index for which it does equal, we break out of the while loop. The I wasn't changed, and I would be less than or equal to -1, and then we return I. Just to be sure, I'm going to check linear search on 19 in L, just to make sure. That's the 7th index, 0, 1, 2, 3, 4, 5, 6, 7. Okay. Okay, so this wasn't too bad. So just in case you're curious about like how in-depth these algorithms can get, in my data 4319 course, so it's a data science course called Statistical and Machine Learning, we currently are, well, basically everything in that class is some sort of algorithm. So here is an algorithm that takes in, so we have handwritten digits here. Each digit is a big slice of numbers where the scaling on the entries of that slice, so it's like a big matrix, corresponds to a number. It's the pixel density, basically the pixel intensity. Okay, so then this is just all looking at stuff, but we can build an algorithm based off of the design with something called a neural net. So this is a neural network. And then we can train this network using an algorithm called gradient descent. There's the error rate, but so let's just this has already been trained. That's why my computer's been running so slow. It's been doing this for my next class. So we predict a label of 3, and the actual label is a 3, and that's it. And the interesting about this algorithm is that it's never seen this 3 before, but it still is able to accurately predict it. Predicts that's a 1, predicts that's an 8, and it predicts that this is a 9 when it's actually a 4, but you can see how it might think that this should be a 9, right? So it hasn't been trained fully yet. Its accuracy is, I think it's 83%. Yeah, so it's roughly 83% accurate on the data it hasn't seen. But the fun thing about this is that it has never seen these pictures, and it learns, kind of like a brain learns, to predict these images. And these types of algorithms are very prominent in today's business society or business applications. For example, when you take photos on your phone of checks, it's the same type of thing here. Self-driving cars make predictions as to whether to brake, turn left, speed up, based off of these same types of neural networks and the algorithms on them. So algorithms are incredibly important for the modern world. Basically everything that you look at on your phone is built around some type of algorithm. And you can see that this thing is pretty accurate. Even at 83% accuracy, it's still getting, I thought that was a 7 for some reason, but it's still pretty accurate. So I encourage all of you that are interested in that type of, those types of algorithms to maybe consider data science as a major or double major along with your CS degree, because there's lots of really cool algorithms that you'll implement with that degree. Okay, so that will be it for today's lecture. Next time we're going to look at more searching algorithms and then also sorting algorithms. And hopefully by the end of today, all of your exams, exam 1 grades will be posted on Blackboard. So just be looking for those. All right, everyone stay safe. And if you have any questions about machine learning and deep learning and data science, feel free to email me, and maybe we can have like a little Zoom meeting on our own to talk about it. I think it's like pretty interesting stuff. So, all right, everyone stay safe, and I will see you next time.
Thank you.